Please don't forget to like, subscribe, and comment. Thank you so much.
Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +2348085095144 to learn more and get started today.
Okay, you should be familiar with how we plot the graphs. I just need you to understand how you can differentiate between a velocity time graph and a speed time graph. Most of the work you did at O level had to do with just velocity time graph, and you didn't really know the difference between a velocity time graph and a speed time graph. So I want us to look at that. But let's look at this question. I'm sharing on this screen. Look at this illustration. I think I can zoom it in to make it bigger. This is not the biggest it can be. Okay, this is a motion of an object that started with an initial acceleration of 6.0 meters per second. Can you see that?
Yeah.
And then later the acceleration reduced to, anyway, it had 6.0 meters per second squared acceleration for 20 seconds. And later the acceleration reduced to 4.0 meter per second squared for 10 seconds. And that speed is maintained for 30 seconds. Now we're asked to calculate the maximum speed attained and then the total distance covered in the first 30 seconds. All right. So, to go about that, it started from rest with this initial acceleration. So U is what?
0.
U is 0. Okay. I think we're even asked to sketch the distance time graph and the acceleration time graph. All right. So it started from rest. The acceleration is 6.0 meters per second squared. It's similar to the things we did earlier. Time is 20 seconds. U is 0. V is what we don't know. And we can apply A equal to V minus C over T to get V equal to U plus AT. And with that we can get V. V is 120 meters per second. And that's for the first part of the motion. You can see what I did? Alright, A equal to V minus C over T to get the final velocity for that first part of the motion to be 120 meters per second. And then the second part of the motion where we are told that it did 4.0 meters per second for 10 seconds. For 10 seconds. 4.0 meters per second squared acceleration for 10 seconds. So let's see what the speed will be at the end of that motion. This was a final speed for the first stage, and it is this final speed that is used starting with for the second stage. Do you understand what I mean?
Yeah.
So the final speed for the first stage becomes the initial speed for the second stage. So we need to now find the final speed, if you like. Acceleration is still 4.0 meters per second. The new acceleration now is 4.0 meters per second squared. 4.0 meters per second squared. Or let me write it in red so it can come out better. The acceleration is 4.0 meters per second squared. You may need to zoom in properly so that you see it better. Okay. You need to zoom in maybe to 200% or as much as you can zoom in to see it better. So this is a new acceleration. The final speed for this first stage of the first stage is now the initial speed for the second stage, because it ended with this final speed in the first stage, which is this used starting with for the second stage. So time is 10 seconds. As the new acceleration is now 4. We apply the same formula, v equal to u plus 80, 120 plus 4.0 times 10. So now we can see that the maximum speed at 10 is 160 meters per second. I think that's clear. Okay, so the other question says the total distance traveled in the first 30 seconds. Total distance traveled, you can find area under the graph if you want to use that. What is this shape? 1, 2, 3, 4. It's not even a trapezium, but we can divide it into 2. Can you see what I'm tracing? You need to look at it from at the top.
Yeah.
Anyway, this is the first stage where it traveled with the initial acceleration of 6.0 meters per second squared. We found the final speed to be 120. Is it not?
Yeah.
The second stage where it traveled with an acceleration of 4.0 meters per second squared, and we found the final speed to be 160. By the way, the first stage, it took 20 seconds. That's why we stopped at 20 here. So I can drop down to 20. It's a rough sketch. So this one, here is 20, and here is 10. The second stage, it did it for 10 seconds. Okay, so the total distance traveled for the first 30 seconds with the area under this graph now, is it not?
Yeah.
Area under in a velocity time graph, the area gives the distance. So, this shape, the entire shape is not a trapezium. That's why I divided it into 2. First triangle, then the second trapezium. The first triangle is half base times height. Half times 20 times 120. And then we find the trapezium and add up. That's what we did. So the first one is a triangle half base times height, which is 1,200 meters. The second stage is a trapezium. If you're not seeing it, you can slow down a bit, the workings.
Yeah.
So the second stage is a trapezium, which is half times sum of parallel sides times height, or the distance between the parallel sides. The area of a trapezium is half times the sum of the parallel sides. These are 120 and 160 times the distance between the parallel sides, which is 10. So we got that 140 or 1,400. So the total distance will be 1,200 plus 1,400, isn't it?
Yeah.
How come I didn't write that down? Then that's what the question asks us to find. Find the total distance traveled in the first 30 seconds. So the summation of the two. And what does that give? Alright, so let me just add them up. So total distance, I don't know, maybe I cleaned it later. Total distance will now be what? That's 1,200 plus 1,400. That's 2,600. 2,600 meters. I think that's it. This plus this. Because it says the total distance for the first 30 seconds. Are you with me?
Yeah.
Okay, so if you're getting that, the next one that I really want us to talk about is this. Okay, first of all, it says the average speed during II. How do you find the average speed? Average speed is total distance over total time now, isn't it?
Yeah.
So total distance is 1,400. Oh, sorry, total distance is 2,600 over total time, which is 30. That one is easy. So that would be 2,600 over 30. Is it not?
Yeah.
Because average speed is total distance over total time. So 2,600 over 30. So we shouldn't bother ourselves about that. You can easily figure that out. That's average speed. total distance over total time, don't forget. Total distance over total time. Alright, in that case, whatever the total distance was, we divide it by the total time, which is 2600 over 30. Alright, now the point that really concerns is of more concern to me at this point is the sketching. So sketch the distance time graph. Sketch. By the way, it says the last stage of the journey was just a constant speed, because it says he maintained this speed. Can you look at the question again?
Speed is maintained for 30 seconds.
Speed is maintained for 30 seconds. So he maintained that speed for 30 seconds. He maintained that speed for 30 seconds. He maintained that speed for 30 seconds, which is this. All right. So, how do we sketch it? This is a velocity time graph. I think I need to zoom out a bit to reveal this better. This is a velocity time graph. How do you sketch the speed time graph? By the way, what is this in a velocity time graph? What does this represent?
Acceleration.
What kind of acceleration?
Constant.
This is constant acceleration. This is a lower constant acceleration, is it not? The first stage is higher constant acceleration. The second stage is lower constant acceleration. The last stage is constant speed. So how should it be sketched? You know, distance time graph acceleration is going to be like this, is it not?
Yeah.
Another constant acceleration. This one should be less steep, you know, and then constant speed. That is for a distance time graph. But you see, when you're sketching this, you need to indicate these values. That's the point. These values obtained, like the first distance is 1200, so it should be indicated. Okay, so we have it. What I needed you to pay attention to is the important details on the graph. Are you seeing what I'm pointing at? Like the first distance, you know, this is the distance against time graph. Distance against time. The first distance was 1200, so you need to indicate that anytime you are sketching a graph, those important details must be indicated. For the first stage, the first distance was 1200, so it should be indicated on the graph 1200 for the distance against time. You get that?
Yeah.
The second stage, the total distance was what? For the second stage, that's at 30 seconds. At 30 seconds, what was the total distance we got? It's still up here. Are you sure you're looking at what I'm circling? It's not showing at your end. Pardon?
2600.
So it should be also indicated. So here is 2600. Now the last stage, that means you still need to calculate the distance for the last stage. The last stage, where it moved at a constant speed. You still needed to calculate the distance for that last stage. You know, I think that one is just speed times time. What was even the maximum speed? What was the maximum speed we calculated? That's 1600, 160 meters per second now. See it towards the left hand side, at the bottom of the left hand side. 160 meters per second. 160 meters per second for how many seconds? it says speed is maintained for additional 30 seconds. Go up a little bit, we see the last part of the question, the last part of the statement. Speed is maintained for 30 seconds. For 30 seconds. So that speed is maintained for 30 seconds.
Yeah.
So 160 meter per second maintained for 30 seconds. What's the distance there? That's
Yeah.
speed times time now. That's a constant speed times time, you know.
Yeah.
Yep. So all I'm trying to say is the distance here, since it's a constant speed, is, you need to scroll up if you're not seeing it. Constant speed is speed times time, v times t, which is 160 times 3. I think that should give 0.84. 3 times 6, 18. So 480 or 4,800. Is it 3 times 0, 0, 3 times 6, 18. 3 times 1 is 4. That's 480. 480 meters. Is it 480 or 4,800?
Wait, what happened to the area on that graph?
No, this is a distance against time graph. Oh.
Oh.
This this is a distance against time graph. So distance is just speed times time. Sorry, is this thing 1,600 or 160? Let me be sure. It looks like it's 1,600. No, that's 160. Oh, 160 for 30. I wrote 3 for 30 seconds. No. So it's 1,000, 4,800. Did you get it?
Yeah.
Anyways, you know the distance for the first one is S is 1,200. For the second one, S is equal to, let me write it with a different color, maybe blue. For the second one, S is equal to, what did we get it first before we added? 1,400. 1,400. S, the distance is 1,400. Okay, that's for the second stage. That's why at this point we plotted 1,200 for the distance. Now that's after 20 seconds. The distance is 1,200. Additional 10 seconds, making 30 seconds, we have another 1,400. Another 1,400. So 1,200 plus 1,400 will give us 2,600. So that's why we have 2,600 here after 30 seconds altogether. Now, this last stage is a constant speed, which we found to be speed times time. You know, you can simply use the formula speed times time, S equal to speed times time, for any constant speed situation. And we found 160 times 30, that gives us 4,800 meters. So that will tell you where this place will be, what this value will be. I'm not sure you're even seeing what I'm pointing at. Are you?
Yeah.
Okay, so where here should be. So to know what this position should be, you need to do 2,600 plus 4,800. You know, that's how we came about 7,400. Because all those positions must be plotted accordingly. You must indicate those key values. 20 seconds for 1,200. 30 seconds after, that's 30 seconds from the start, now 2,600. 60 seconds from the start, now 7,400. So that's plotted. Can I continue? I think the final thing says we should find the acceleration against time graph. Acceleration against time graph. Acceleration against time graph. Are you ready for that? Okay, so it's easy because don't forget that this, scroll up a bit, let me, so that I can just tell you what to do. Scroll up a bit. Scroll up a bit, yes. This is velocity against time. And the first stage is constant acceleration of what? 6.0 meters per second, is it not? per second squared. 6.0 meter per second squared. The second stage is a constant acceleration of this second stage is, okay, please can I just write it inside it? Let me write it inside the shapes. The first stage is a constant acceleration of 6.0 meter per second squared. The second stage is a constant acceleration of 4.0 meter per second squared. And what's the acceleration of the third stage? Let me write it in green. What's the acceleration of this third stage? No, maybe red. 0 meter per second squared. So if we are asked to plot the acceleration against time graph, you can easily do that now. The acceleration against time graph is easy now. Simply first stage is constant acceleration. For 20 seconds, we're just going to plot a constant acceleration of 6.0 meter per second squared. Additional 10 seconds, making 20 to 30. 20 seconds to 30 seconds, we plot an acceleration of 4 meter per second squared. Then the last 30 seconds, that's from 30 to 60, acceleration of 0. That's why the graph is like this. Can you see it? Below, down, down, down. Go to down, down, down. I think you need to go to the left. Go to the left, you find it left. Are you seeing it left?
Yeah.
This is what I'm talking about.
Yeah, I can see.
Alright, so the first is acceleration of 6, the second is acceleration of 4, the last is acceleration of 0. First 20 seconds, acceleration of 6, because this is acceleration against time. The next 10 seconds, that's up to 30 seconds, that's from 0 to 30, starting from 20 to 30 seconds, acceleration of 4, from 30 to 60 seconds, acceleration of 0. Okay, having said that, there's something very important I need you to take note of. All these things I wrote here is very, very vital. Look at this. Here. You see what I circled? You already know that this is a constant acceleration, is it not?
Yeah.
Now, in a velocity time graph, I've mentioned that to you earlier. In a velocity time graph, anytime the graph is above the time axis, it is motion in the forward direction. I remember when I told you this some time ago, I told you when you get to A levels, we talk about this in more details. If the graph is above the time axis, it is motion in the forward direction, like moving forward. Now, if the graph is below the time axis, it is motion in the backward direction, that's reversing. That's for a velocity against time. So all of this is the time axis. All these are motion in the forward direction. What do you always call this in a velocity against time? So this is acceleration in the forward direction. What do you normally call this in a velocity against time? So this is a deceleration in the forward direction. Now, if it is below the x-axis, now this is now, if it is going this way, it is actually a deceleration. So you say the opposite. Now take note of what I just said. This is a deceleration in the backward direction. You know, it would have been, if it was above the time axis, this would have looked like an acceleration, is it not? Now, because it is below the time axis, it's actually a deceleration in the backward direction. While this one that would have looked like a deceleration is now an acceleration in the backward direction. Take note of that. Also, above the time axis, you know, what would you have called here, by the way? What I'm pointing at?
constant speed.
Constant speed. So this is constant speed in the forward direction. Constant speed forward. While this one that is below it is constant speed in the backward direction, isn't it?
Yeah.
Okay. I think if you were to plot it a distance against time, let me zoom this thing out a bit so that we can capture all. Now watch me. This graph that I have here, can we plot it in a distance against time graph? This graph, this velocity time graph here, let's change it to a distance against time graph. Let's change it to distance against time graph. How will you plot here? A to B in a distance against time graph.
A to B. Oh, distance against time.
Yeah.
Acceleration and distance.
This, remember, this is constant velocity. A to B is constant velocity.
Oh,
Forward direction.
you draw it
Like it will look like this now, is it not?
yeah.
Now, what about B to C, which is now moving backwards? For a distance against time graph, it will be this, is it not?
Yeah.
You remember all this? Anyway, I usually tell you that this is constant speed reversing, is it not? This, yes, B to C is constant speed when it's reversing. Do you agree with me?
B to C.
Yes?
Oh, yeah.
Yeah, B to C is constant speed when it's reversing. A to B is constant speed when it is going forward. A to B. I said all of that to tell you that this graph in velocity against time graph is this in distance against time graph. So the point I want to make is, while we can use discontinuous lines for velocity against time graph, the distance against time graph does not have this continuous line, even when the direction of motion changes or reverses. Let me explain. Let me explain. Tell me again what's happening in A to B. Constant speed in the forward direction. At this point, you need to specify constant speed in the forward direction, is it not? Maybe the value of the constant speed would have been given, maybe if it is constant speed of 10 meters per second in the forward direction. Good. So this is constant speed in the forward direction. That's A to B. What is B to C? Constant speed. B to C is constant speed in the backward direction. There's no way you can get B to C after A to B without this graph breaking. We call that discontinuous graph. It has to break first before you can get that. You find that in velocity against time. It will definitely break. But if you plot it in distance against time graph, there's no point for that break. Breaking means like you have a dot 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 and then you have another one. No, it doesn't. In fact, distance against time graph is always above the time axis. Whether it is forward or backward, it's always against the time axis. Above the time axis, as you can see. So it doesn't have a neck and form another one below it. There's no need for that. So that's what I wrote here. We can use discontinuous line for velocity against time, but distance against time graph is always a continuous line, even when the direction of the motion changes. Anyways, I need to emphasize this with a question, one of the questions you have. Let's go to the other Jamboard, Physics 6. Now this is a distance against time,
Yeah.
What's happening between 0 to, how many seconds is this? Maybe 3 seconds. For this distance against time. Can I zoom it in? Let me zoom it in to 100%. What's happening to between 0 to 3 seconds? This is second 3.
Acceleration.
This is acceleration, which is constant acceleration. What's happening between 3 seconds to, can we call here 6? No. In between maybe 7. Let's call here 7. Here's 7. What's happening between 3 seconds to 7 seconds?
Constant speed.
Constant speed, because it's a straight line. And what's happening here
Where?
between 7 seconds to 15 seconds? Deceleration. Now you need to be telling me, let's start again, because you need to tell me forward motion and backward motion. Can we start again from 0 to 3 seconds, please? This is a very good review. From 0 to 3 seconds is what?
Acceleration.
Acceleration in the forward motion, is it not?
Yeah.
3 to 7,
And constant.
constant speed forward motion. 7 to 15,
Deceleration in the forward
deceleration in the forward motion.
motion.
Now 15 to here should be about 23. Here is about 23.
Acceleration in the backward motion.
Acceleration in the backward motion, because you can see that it's getting steeper. It's getting steeper. So it's acceleration in the backward motion. This was acceleration in the deceleration, because it's getting less steep. From 7 to 15 it was getting less steep. So deceleration in the forward motion. Now 15 to 23, that's acceleration, is getting steeper, but in the backward motion. Yes. What again? What again do we have? Anyways, can I just, so that we don't waste time, what's happening between 27 to 30?
27 to 30 is
Rest, that's the distance against time graph. So this rest. Alright, you see the way this thing is converted to velocity against time graph. So the first part is constant velocity, constant acceleration. This is now a velocity against time graph. So this is constant acceleration, forward motion. So it's 0 to 3. Let me also indicate 3, 7, 23, 27. So 0 to 3, constant acceleration is forward motion. 3 to 7, constant speed forward motion. As you can see, this is constant acceleration forward motion. That's it. That's 0 to 3. 3 to 7, constant speed forward motion. 7 to 15, this constant deceleration, still forward motion, constant deceleration, forward motion. Now when it is now changing direction, it now goes under the time axis, that is from 15 to 23. 15 to 23 is 15 to 23 is no, 15 to 23. Yeah, 15 to 23. I'm right. 15 to 23 is what? What did you say again? It is
acceleration.
acceleration in the opposite direction. Can you see the way it is?
Yeah.
That's what I told you. Now, acceleration in the opposite direction will look like this. And what is this one? Just tell me what 23 to 27, what it is. I like that. This graph is a very good one. Tell me 23 to 27 for a velocity time graph, what this means.
Deceleration.
Yes, so this is deceleration in the opposite direction. That's why this is curving this way. Deceleration in the opposite direction. That's a deceleration. So 23 to 27 is a deceleration in the opposite direction, of course. 27 to 30 is rest, which is zero speed, rest. All right. And of course, you can easily get the acceleration against time. It's easy. You find the acceleration here, you get it for the first one. Am I right?
Yeah.
The acceleration here is whatever this is, 15 over whatever it is. Okay, 15 over, what is this value? Because what I'm getting here looks like 3 or 4. Anyway, whatever it is, whatever this value is over 3, you get this one. What? See where I'm tracing? What's the acceleration here?
Zero.
0, because it's a constant speed, so that's why the acceleration is 0 here. Now, what is this from 7 to 15? That's a deceleration, is it not?
Yeah.
A deceleration, even up to 23. Oh, anyway, this is a deceleration, and you know a deceleration is a negative acceleration. Do you know?
Yeah.
So that's why it is now on the negative side of the acceleration graph up to here. And then now this is another, what do you call this?
Deceleration. Zero acceleration.
No,
Deceleration.
this should be a deceleration. In the other direction, deceleration in the other direction,
Yeah.
deceleration in the opposite direction, deceleration in the opposite direction, and that's why it's coming up here. But I don't want that to confuse you or to make it difficult. Anyway, this is where it is explained. Like I just told you, if you look at this, you will see the explanation. You can go through it at your convenient time. It's part of all the things I said. All right, let's go to the last page. I want to show you something. I just need you to know how to change velocity against time graph to speed against time graph. Now, are you ready?
Yeah.
In the forward direction, there's no change. Once it is in the forward direction, you don't have any change because this is velocity. You know, this is velocity in the forward direction, is it not? By the way, what is this, by the way? This is a velocity against time graph. Describe this graph.
Acceleration.
Constant acceleration in the forward direction.
Yeah.
So the speed against time is also constant acceleration in the forward direction. It looks like this. You know, it is in the same direction. But what is this one from here to here? Let me letter it A to B and then B to C. What is A to B?
A to B is constant acceleration going the opposite direction.
No, remember what we said. If it is going this way, it's not a constant. It's not an acceleration.
Oh, constant deceleration.
This is constant deceleration. I need to explain something to you. Oh my goodness. Okay, no problem. A to B is a constant deceleration.
Yeah.
B to C is what?
B to C is constant acceleration.
Does that make sense here?
Yeah.
Constant deceleration. constant acceleration, constant deceleration, constant acceleration. For a speed against time. In fact, because speed does not concern itself with direction, it's only size, magnitude. Are you listening to me?
Yeah.
You don't have it you don't have it below or on the other side of the time axis. Speed, we are not interested in direction in speed. Speed is a scalar quantity, unlike velocity that is a vector quantity. Velocity being a vector quantity, you have to have the direction specified. When it is in one direction, it should be in at one side of the time axis. If it is in the other direction, it should be at the other side of the time axis. So like remind me again, let me label it. What you said, let me label it for proper explanation. A to B, you said is what? Let me write it. Say it again. A to B is what? As you can see. Constant deceleration in the opposite direction or in the reverse. Yeah. If it looks like this or down, it is actually a constant deceleration. So you said B to C is what? B to C. B to C is what? So B to C is constant acceleration. In, let's call it forward direction. Since this one is the reverse, the other one is forward. So now for a speed against time graph, all of that, you can see this is constant deceleration A to B. So that's why B, it looks like that. It's A to B. You know, sorry, A if you like. And then to C. So A to B is constant deceleration, as you can see. And B to C is constant acceleration. Now, because speed has nothing to do with direction, all of them are above the time axis. All of them are on one side of the time axis. Whether above or below, they are all on one side. That's all I need you to take note of. Okay, having said that, let's attempt some questions. Let's quickly attempt some questions. Let's practice this. Go to page 4. Let's see this challenge. Are you there?
Yeah.
This challenge, and you may need to zoom in properly to see it better. So the graph shows the velocity of an object traveling in a straight line during a 10-second time interval from 0 to 10. After how long did the object change direction? Tell me. After how long did the object change direction? Oh, undo, please.
Yeah.
Okay. So after how long did the object change direction?
After 6 seconds.
Beautiful, after 6 seconds. Because for a velocity against time, to change direction, it has to now be under the time axis. So after 6 seconds. You know, if somebody who is not enlightened in this might think it is 3 seconds or even 5 seconds when it's now moving the other way. You know, from 0 to 6 seconds, it is still in the forward direction. I hope you know, because it is above the time axis. From 6 seconds to 10 seconds, that's when it is now moving in the opposite direction. Okay, so you are absolutely right. This is after 6 seconds. Work out the total distance traveled by the object. I like this. I like this. Because after the distance, they ask us to find the displacement. You will see. They say, you know, there's a difference between distance and displacement. Distance is scalar. Displacement is vector. So direction is important in displacement. So let's work this out. I like this. This is a question that can explain something I have in mind. So first of all, work out the total distance traveled. Total distance. Total distance is the summation of all the area under the graph. The summation of all the area, whether above or under the graph. This is the reason. We've talked about this before, if you remember, just for emphasis. Just for emphasis, let me remind you. So this is A, this point is B, this point is C, this point is D. Assuming A to B is 5 meters, B to C is 8 meters. What's the total distance traveled, or what's the distance traveled from A to D? Assuming there was an instantaneous change here, which didn't count for anything onto D. What's the distance traveled from A to D? Distance, you know, from A to D is what? Distance is this distance, yes. Pardon? 21. That's 5 plus 8 plus another 8, so 21. 5 plus 8 plus 8, which is 21 meters. So where was the displacement from A to D? Displacement from A to D is just 5, because displacement is where you are measured from where you were. Where you are is here, and where you were is here. You measure from where you were is just 5 meters, no matter all the places you moved. So displacement is just 5. You can also get that displacement by finding the total distance, and you subtract it from the one under. You know, total distance. Anyway, let me not overflog it. Let's just go to the question. So work out the total distance. Total distance is then, you know, this is velocity against time. So the entire area under the graph, everything is about distance, isn't it?
Yeah.
So what's this area? I will shade in yellow. What's this one? I will shade in blue. What's this one? I will shade in green. What's this one? This looks like a trapezium. 1, 2, 3, 4, because that's a trapezium. I can shade all of them in what? What other color? Red. In red. So the one for the blue, the yellow is what? Half base times height. Half times 2 times 3. That's 3 meters. The one in blue is 1 times 3, that's length times breadth, which is 3. The one in green, half base times height, that's 3 times 3. 3 times 3, that's 9, right? Oh, half base times height, sorry. That's 4.5 divided by 2. That's 4.5, right? So thank you for the observation. 4.5 meters. And finally, the one in green, in red, which is under, is half times sum of parallel sides. The parallel sides are 4 up to 10. That's from here to here is 4, and from here to here is 2. Am I right?
Yeah.
So half times sum of parallel sides, 4 plus 2, then times the distance between parallel side is 2. Am I right?
Yes.
That's from here to here, 2. Half times sum of parallel sides, 4, that's 6 to 10, 4. 8 to 10 is 2. So 4, half times 4 plus 2, yeah, 4 plus 2. Then times the distance between parallel sides, which is 2, from here to here, 2. Alright, so that will give us 6. Then that's 6 meters. So the total distance is 6 plus 3 plus 3, that's 12 plus 4.5, that's 16.5. Am I right? 16.5. So this gives 16.5 meters. So it says now work out the displacement from the starting point to 6 seconds. What's the displacement from here to 6 seconds? It didn't change direction, so it's the same forward motion. Displacement is still everything, is it not?
Yeah.
So what's the displacement from the starting point to the 6 seconds? Yes, answer this question. CI. What's the displacement? Okay, so what did you say is the displacement after 6 seconds? Are you there?
2.5.
What did you say?
10.5.
Okay, 10.5, that's 3 plus 3 plus 4.5, the whole forward motion. So 10.5, 3 plus 3 plus 4.5, which is 10.5. Yeah, 10.5 meters. All right, what about the displacement after 10 seconds?
After 10 seconds.
Yes, after the whole thing.
Isn't that like 4.5?
No.
Wait. Sorry. 6. Right. 5.5.
And how did you get it? Up
5.5.
minus 6. So this, in fact, the bigger minus the smaller, as the case may be. For the forward motion, it is 10.5. For the backward motion, it is 6. That's 4.5. So 10.5 minus 6, which is 4.5. Okay, so that's the displacement. You know, if we drew it, we would have also seen, just like it worked came back, and then you eventually find displacement is where he was measured to where he is now. It's just like somebody walked 10.5 meters. Let me just illustrate. If someone walked 10.5 meters from A, walked 10.5 meters, and then to B, then from B, where he walked backward by 6 meters. If you walk backward by 6 meters to come to C, so what's his displacement from A to C now?
From what?
From A to C now, what's his displacement from A to C? A to B was the forward motion, which you calculated 10.5, and B to C is the backward motion, which is 6. Oh, so A to C is simply, as you rightly said, displacement, from A to C is simply 10.5 minus 6, is it not?
Yeah.
Which is 4.5. But the total distance is 10.5 plus 6. Is that what we did? We got, okay, they didn't ask us for the total distance from A to C. But I think there was a question like that. Did we solve that? Yeah, that's it. From A to C, we did that earlier. Work out the total distance. That's how we got 16.5 meters. That's 10.5 plus 6. Did that make sense?
Yeah.
Any other one you will be able to solve it. There's nothing in this. You should know. There's really nothing serious in all of these questions. Okay, this part says we should sketch the speed against time graph for that motion. Speed against time graph for this motion. The speed against time graph. Speed against time graph. So this is how it should look. Let me put it here. Let me draw the graph like this. Represent 2 here, 3 here, then 6 here. No, it's too far. 6 here and 10 here. This is now speed against time. Speed in meter per second against time in seconds. Okay, to draw speed against time graph, okay, we also have 0 and 3 here. Now the first motion, which is from 0 to 2 seconds, is constant acceleration in the forward direction, so it's going to be this. The second motion is constant speed for 1 second. Let me dot this down. Dot. So the first motion is forward constant acceleration, or constant acceleration in the forward direction. The second motion is constant speed, also in the forward direction. The third motion is constant deceleration, also in the forward direction, if you remember. So one more time, this is constant acceleration in the forward direction, or let me represent it here. Constant acceleration in the forward direction, constant speed in the forward direction, constant deceleration in the forward direction. Now this is now constant acceleration in the backward direction. 6 to 8 Oh, I didn't even represent 6 to 8 before 10. So this is 8. This is 8. This position is 8. So 6 to 8 is constant acceleration in the backward direction. Constant acceleration in the backward direction. And since for velocity, speed against time, those things don't count, it has to be in the same direction. Those in the for speed against time, it has to be in the same on the same side of the axis. So remember, here is 2. This place is 2, so it has to be here. And on 2, let me represent it at 2. Let me show you. Then down. Let me explain again. Constant acceleration in the forward direction, that is here for speed against time. Constant speed in the forward direction, that is here. Constant deceleration in the forward direction, that is here. Now from 6 to 8, from 6 seconds to 8 seconds, it is constant acceleration in the backward direction. Constant acceleration. So since speed against time we're not concerned about direction, we are only concerned about magnitude, and the magnitude is constant acceleration. So that's why it's going to be like this. Constant acceleration from 6 to 8 is a constant acceleration. Yes, it is in the backward direction, but for speed against time, speed is a scalar quantity, direction is not important. All we need is that what this thing means, and this thing means constant acceleration. So this is constant acceleration. So constant acceleration up to 2. Constant acceleration. And then the final stage of the motion, which is this, is constant speed. Even though it is constant speed in the backward direction, but we are not interested in the direction, so it will still be on the same side of the time axis. So this is constant speed. So this is how it will be. Alright, so this is a speed against time graph, while this is the velocity against time graph. Constant acceleration in the forward direction, constant speed in the forward direction, constant deceleration in the forward direction, constant acceleration in the backward direction, that's 6 to 8, constant speed in the backward direction. That's it for speed against time. Constant acceleration in the forward direction, constant speed in the forward direction, constant deceleration in the forward direction, also constant acceleration, even though this one is now in the backward direction, but we're not interested because it's speed against time and then constant speed. So this is how it will be for the speed against time graph. This is how it will look for the speed against time graph. There's nothing serious in all of these questions. Any other one you should be able to solve. You can solve. Let's even see this 7 if it makes sense. If it doesn't make sense, there's something in this 7 that I think, hey, you figure that out. It's not a big deal. Let's even do that. So a particle moves 100 meters in a straight line. It looks like the entire thing is 100 meters. The diagram is a sketch. The particles start from blah blah blah, moves 10 meters per second. Okay, start from rest, it moves 10 meters per second in 3 seconds and accelerates to a velocity of 10 meters, okay, in 3 seconds. The velocity of 10 meters is maintained for 7 seconds. That's after 7 seconds, now at 10. And then the particle decelerates to rest in 2 seconds, down to 12. Find the value of u. How will you even find the value of u? It's easy now, is it not? That's not a difficult thing. That's not a difficult thing to find u. You can find this area so that we subtract it from the whole distance traveled. Are you getting me?
Yeah.
This is a trapezium, am I right? 1, 2, 3, 4. Yeah, that's a trapezium. So what's this whole distance? This whole distance. Are you ready?
I thought class was over.
And let me just conclude this so that we're done. Because I need to be sure you know how to do this. What's this whole distance so that we can round off? Half times sum of parallel sides. Where a parallel side 3 to 12 is 9. That is from here to here. And then 3 to 10 is 7. Plus 7. Then times height, which is distance between parallel sides, that's 10. Sorry. So times 10. And that gives us 5 times 12. Is this 60? So 60 meters. So this whole area is 60 meters. And we are told that it traveled a total of 100 meters. Are you getting it?
Yeah.
So the remaining area is what? The one I'm shading in blue. The guy traveled a total of 100 meters.
Oh,
With, okay, the remaining area is 100 minus 60, which is 40 meters. Oh, we made a slight mistake here. Here, we made a slight mistake here. 9 plus 7 is actually 16. 16 times 10 is 80. So this area shaded in red is 80 meters. And the entire, so this distance from 3 seconds to 12 seconds is 80 meters. And the entire distance covered from 0 to 12 seconds is 100 meters as given. So it should actually be 100 minus 80, which is 20 meters for this blue one. So this blue one is actually 100 minus 80, 20 meters. And so to find u, this is also a trapezium. 20 is equal to half times sum of parallel sides u plus 10, this u plus this 10, 10 times height. So we can easily get the height. Remember, is the distance between the parallel sides. I think we can quickly solve that. This gives us 20 is equal to half times, this will be u plus 10 over 2, or if we multiply both sides by, anyway, let me just multiply both sides by 2, that will give us 40 is equal to 3u plus 30. Just solving this, multiply both sides by 2, that will give us 40 equal to 3u plus 30. And that will give us 40 minus 30 equal to 3u. This gives us 10 equal to 3u, or u will be equal to 10 over 3, which is 3.33 meters per second. So the initial speed is 3.33 meters per second. The other question says find the acceleration of the particle in the first 3 seconds. We found this initial speed to be 3.33. Final speed is 10. Time is 3 seconds. So this acceleration will now be a is equal to v minus u over t, which is equal to 10 minus 3.33 over, so let me zoom it in properly. Zoom in to have that clearer. So this will be 10 minus 3.33 over 3.33 all over 3, which is the time, divided by 3. Alright, so that's what we can do to find the acceleration as B for the first 3 seconds.
Please don't forget to like, subscribe, and comment. Thank you so much.
Welcome to Like Learning School, your premier online education platform. At Like Learning School, we are dedicated to helping students and learners unlock their full potential, providing them with the foundation, support, and guidance they need for academic excellence. Our platform caters to 2 main target audiences. Firstly, we work with school children of all ages, offering academic follow-up and accountability partnerships. Our seasoned tutors provide personalized attention to ensure students stay on track and reach their goals. Secondly, we support students and learners who are preparing for internal, external, entrance, or professional examinations. We offer comprehensive and well-structured support to help them achieve outstanding performance in their exams. Our robust virtual courses are designed to keep students engaged and motivated. With interactive videos showcasing our teaching sessions, students actively participate in the learning process, making education enjoyable and effective. But that's not all. We believe in personalized education. Our students have access to personalized tutorial sessions, whether online, physical, or hybrid, tailored to their unique learning needs. Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +234 808 509 5144 to learn more and get started today.